It is late and the room is dark. You have turned off the lights, settled into the quiet, and the world outside has receded to a low hum, or perhaps to silence. In this darkness, something is moving through you, not metaphorically, not as a figure of speech. Billions of particles, subatomic, invisible, fundamentally unlike the matter that makes up your body, are passing through you every second. They do not interact with your skin or your bones. They leave no trace. They stream through the walls, through the floor, through the ceiling, through the dark air, as though none of it were there. And yet this substance, whatever it is, accounts for about 85% of all the matter in the universe. Everything else, every star, every planet, every galaxy, every atom in your body, every atom in every living thing that has ever existed, is the smallest fraction of what is actually out there. We can map this invisible substance. We can weigh it. We can trace the hand it played in building the cosmos, and we have no idea what it is. Hello, and welcome to Sidereal. Tonight, a single question. What is the invisible substance that makes up most of the matter in the universe? The substance we can weigh and map and trace back to the first moments after the Big Bang, and still cannot name. By the end of this, you will know how we found it. You will know the names of the people who found it, often by accident, often while being ignored, and you will understand why not knowing what it is may be the most honest thing we have ever learned about the cosmos. The number is worth sitting with. If you take everything we can see with our telescopes, all the stars in all the galaxies, all the gas and dust between them, all the planets, all the comets, every atom that emits or reflects or absorbs light, and you add it up, you arrive at something that takes a while to accept. All of it, the entire visible contents of the universe, amounts to less than 5% of what is actually there. The precise figure, from the most sensitive measurements we have ever made, is about 4.9%. The rest is divided between two things we do not understand. One of them, dark energy, accounts for about 68% of the universe's total mass and energy, and it is a story for another night. It is not matter at all, but something stranger, a property of empty space itself that pushes the universe apart and drives its expansion ever faster. The other, the subject of this one, accounts for about 27%. That is dark matter. It outweighs ordinary matter by a factor of roughly 5.5 to 1. For every kilogram of atoms in the universe, every proton, every neutron, every electron, there are about 5.5 kilograms of something else, something that is not made of atoms at all. It is worth letting the full accounting settle for a moment. Stack the three together. The dark energy, which we do not understand, is the largest share. The dark matter, which we also do not understand, is the next. And the ordinary matter, the only part we do understand, the part that makes up everything we have ever seen or touched or named, is the thin remainder, less than a 20th of the whole. We have built our entire science, our chemistry and our biology, and our daily intuition about how the world works on that small remainder, and called it the universe. The honest description is that we understand the rounding error, and the main quantities, the dark matter and the dark energy that together are 95% of everything, remain almost entirely unknown. Tonight is about the larger half of that ignorance, the matter we can weigh and map and cannot name. In your own body, the numbers are harder to feel, because dark matter is spread so thinly. The local density near the Sun is estimated at roughly 1/3 of a proton's mass in every cubic centimetre of space. That is extraordinarily faint. A cube the size of the Earth would contain only about 0.5 kilogram of it, but the particles, if they are particles, are moving fast, hundreds of kilometers per second, and they are everywhere, and a human body presents a wide target. The flux through you is enormous. In the time it takes to draw a single breath, billions of these particles have entered your body and left it again, and not one of them has disturbed a single atom of your tissue. You are, in the most literal sense, permeable to the majority substance of the universe. That faint local density is the thin inner edge of something vast. Our galaxy, the Milky Way, sits at the center of a halo of dark matter that dwarfs the bright spiral we can see. The luminous disk, the part with the stars and the dust lanes and the glowing arms, is perhaps 100,000 light-years across. The dark halo wrapped around it reaches out many times farther, a great invisible sphere that may stretch most of the way to our neighbouring galaxies. And it is heavy. Add up all the stars in the Milky Way, all 200 or 300 billion of them, all the gas and dust between them, and you account for only something like a tenth of the galaxy's total mass. The rest, the overwhelming majority, is the dark halo. We do not live in a galaxy of stars that happens to contain some dark matter. We live in a galaxy of dark matter that happens, at its luminous core, to contain some stars, and we are among them near the inner edge, looking outward through a thin-lit disk into a darkness that is most of what we are part of. This is not a metaphor for loneliness or for the limits of perception, though it is easy to reach for those. It is a measurement. It is a physical fact, as real as the chair beneath you or the air in your lungs, and the gap between how precisely we can state it and how completely we fail to explain it is where the whole story lives. There is a particular strangeness to this, worth naming clearly. In most of science, ignorance and precision go together. The things we cannot measure well, we also cannot describe well. But dark matter is the opposite. We can write down how much of it there is, to within a percent or two. We can map where it sits across the whole sky. We can run the clock backward and watch it shape the infant universe. We can do all of this, and we cannot answer the simplest question a child would ask, which is, what is it? By most reckonings, this is the largest unsolved problem in physics. Not the most fashionable, and not the most discussed, but the largest, because it concerns the majority of the matter in existence, and we are missing the whole of it. It is also a problem that has outlasted nearly everyone who has worked on it. The first hints came more than 100 years ago. The first clear measurement came more than 90 years ago. The people who made the early measurements have died, and the people who built the great underground detectors of the 1980s have retired, and still. The question stands, more sharply posed than before, but no closer to an answer. There is something almost steadying in that, on a night like this. Whatever else is true, this particular mystery is patient. It was here before you were born, and it will be here when you wake. The question that comes first is fair. How do we know any of this, if the thing we are talking about does not interact with light? It does not shine. It does not cast a shadow. It does not reflect or absorb or scatter light, or radio waves, or X-rays, or radiation of any kind. That is the definition of the word dark. If you placed a lump of it on a table in front of you, and you cannot, but if you could, you would see nothing. The table would appear empty. You could pass your hand through the space and feel nothing. Every instrument that works by detecting light, from the human eye to the most sensitive camera ever built, would register only absence. And yet we are confident it is there, not because we have a theory that demands it, though we do, but because we have measured its effects in ways that do not depend on any theory. The evidence arrives from several directions at once, each one independent of the others, each one converging on the same conclusion. The universe behaves as though it contains about 5 times more mass than we can see, and it behaves this way on every scale we have ever examined, around single galaxies, inside clusters of galaxies, and across the entire observable cosmos. This convergence is the heart of why dark matter is taken seriously, and it deserves to be stated plainly, because it is easy to imagine that one piece of evidence has simply been over-interpreted. It has not. If the only sign of dark matter were the rotation of galaxies, one could reasonably wonder whether we had misunderstood how galaxies spin. If the only sign were the motion of clusters, one could wonder whether the clusters were somehow not as settled as we assumed. But the rotation of galaxies, the motion of clusters, the bending of light, the pattern in the oldest radiation, the very existence of galaxies in the time available, and the agreement of the early chemistry, all point, independently, to the same missing mass and to very nearly the same amount of it. These measurements were made by different people, with different instruments, resting on different assumptions, separated by decades. They did not have to agree. There was no reason, in advance, that a number read from the spin of nearby galaxies should match a number read from light that left the universe 13 billion years ago. And yet they match. When that many separate roads lead to the same place, it becomes very hard to believe the place is not real. The idea did not arrive all at once. It crept in at the edges for decades before anyone took it seriously. As early as 1904, in a series of lectures, the British physicist Lord Kelvin estimated the number of stars in the Milky Way from the way they move and concluded that many of them must be dark, too faint to see. 2 years later, the French mathematician Henri Poincaré responded to Kelvin's work in print and used a phrase that translates directly as dark matter, matière obscure, weighing whether there was a great deal of it or very little. In the 1920s, the Dutch astronomer Jacobus Kapteyn tried to measure the total mass in our corner of the galaxy from the motions of nearby stars. And in 1932, another Dutch astronomer, Jan Oort, did something similar, studying how stars bob up and down through the plane of the Milky Way, and found a hint that there might be more mass holding them than the visible stars could supply. But all of these early astronomers meant something ordinary by the term. They meant cold gas that did not glow, dust that blocked starlight, planets too small to reflect much light, dead stars that had cooled into darkness. They were not imagining a new kind of substance. They were imagining ordinary matter that happened to be dim. The shift to something stranger, something not made of atoms at all, would take another 40 years, and it began not with a single galaxy, but with a swarm of them, and with a man whom almost no one wanted to listen to. The Coma cluster lies about 320 million light-years from Earth, in the constellation Coma Berenices. It is a swarm of more than 1,000 galaxies, a dense knot in the cosmic web, all of them bound together by gravity. Through a telescope it is quietly beautiful, a field of soft elliptical smudges, each smudge a city of hundreds of billions of stars, all of them hanging together in the dark. The man who first weighed it properly was a Swiss astronomer working in California named Fritz Zwicky, and to understand why his discovery was ignored for so long, it helps to understand the man. Zwicky was born in 1898 in the Bulgarian port city of Varna to a Swiss father and a Czech mother. He grew up in Switzerland, studied mathematics and physics at the Swiss Federal Institute of Technology in Zurich, and in 1925 he crossed the Atlantic to take a position at the California Institute of Technology. He would stay there for the rest of his working life, a tall, blunt, relentless presence in the astronomy department, producing ideas at a rate his colleagues found both exhausting and, very often, infuriating. He was not a gentleman. He referred to astronomers he disliked, which was most of them, as spherical bastards. The insult, he explained, relied on the fact that a sphere looks the same from every angle, so that no matter how you examined these people, they remained bastards. He performed push-ups in the middle of lectures to demonstrate his physical fitness, which he believed went hand in hand with intellectual rigor. He made enemies the way other people make small talk, and he was, by a wide margin, one of the most original astrophysicists of the 20th century. In the same period that he was looking at the Coma cluster, Zwicky and his colleague Walter Baade coined the word supernova and proposed that these vast stellar explosions could serve as standard candles for measuring distances across the universe, a method that would one day reveal that the cosmic expansion is accelerating. In 1934, only 2 years after the neutron itself was discovered, the two of them predicted the existence of neutron stars, objects so dense that a teaspoon of their material would weigh as much as a mountain. Zwicky also proposed, before anyone else, that galaxies could bend the light of objects behind them, acting as enormous lenses. Every one of these ideas would eventually be confirmed. None of them was accepted in his lifetime. He was simply too far ahead and too difficult to be near. There was more to him than the famous predictions. For years, working at the great telescopes on the mountains above Pasadena, Zwicky systematically hunted and catalogued galaxies and clusters of galaxies, eventually compiling a vast multi-volume catalogue of tens of thousands of them, a labour of patient observation that underpinned decades of later work. He discovered more supernovae by eye than anyone of his generation. During and after the Second World War, he organised the shipment of books and equipment to ruined scientific libraries across Europe, an act of generosity that sat oddly alongside his savagery toward his colleagues. He held strong, idiosyncratic philosophical views about how science should be done, championing what he called the morphological method, a deliberate effort to think through every possible form a phenomenon could take before settling on an answer. He was, in short, neither a simple genius nor a simple crank, but a genuinely strange and powerful mind that the institutions around him never quite knew how to hold. The Coma measurement was his most important, and the most ignored. The method was simple in principle. If a cluster of galaxies is held together by gravity, if the galaxies are orbiting one another rather than flying apart, then the speed at which they move must be balanced by the total mass of the cluster. Too little mass, and the galaxies would have escaped long ago. Too much, and they would have already fallen together. By measuring how fast the galaxies move, you can calculate how much mass is needed to keep them bound. Zwicky used a tool from physics called the Vera theorem, which relates the average speed of the members of a bound system to the total mass holding them in place. He measured the velocities of 8 galaxies in the Coma cluster. A small sample by the standards of any later era, but enough. They were moving fast. Their speeds scattered across a range of about 1,000 kilometers per second. To hold galaxies moving that fast inside a cluster of that size, the total mass had to be enormous, far larger than anything the visible stars could account for. When Zwicky added up all the light from all the galaxies in the cluster and converted it into a reasonable estimate of mass, he found that the stars supplied only a tiny fraction of what was required. The discrepancy was something like a factor of 400. The logic is the same one that lets you weigh the sun by watching the Earth go around it, run in reverse. A planet's orbital speed tells you how much mass it is orbiting. Speed up the planet without adding mass, and it would tear loose and fly away into space. So when you see something orbiting fast and staying bound, you know there must be enough mass to hold it. Zwicky's galaxies were the planets. The whole cluster was the central mass, and the galaxies were moving so fast that the visible cluster simply could not hold them. Either the galaxies were a temporary, flying apart accident that happened to be passing through at the moment humans evolved to look, which seemed absurd, or there was far more mass present than anyone could see, quietly doing the holding. Zwicky drew the second conclusion, the reasonable one, and was ignored for it. He wrote in a Swiss physics journal in 1933 that if this result held up, it would mean that dark matter was present in the cluster, in far greater quantity than luminous matter. He used the German phrase Dunkel Materie, dark matter, and he meant it as a physical substance, invisible, gravitating, and dominant, not a metaphor. Not a placeholder for some measurement error, a thing that was actually there. The community did not confirm it and did not pursue it. 3 years later, in 1936, an American astronomer named Sinclair Smith measured the mass of the Virgo cluster by a similar method and found the same kind of excess, a quiet corroboration that should have raised an alarm. It did not. The reasons were partly technical, because measuring galaxy velocities was hard and the uncertainties were large. But they were also social. Zwicky had alienated nearly everyone whose attention he needed. His result was easy to set aside, because he was easy to set aside. He died in 1974, just as the wider evidence for dark matter was finally beginning to turn. He did not live to see his neutron stars confirmed in the pulsars discovered in the late 1960s. He did not live to see the first gravitational lens observed in 1979. And he did not live to see the substance he had named in 1933 become understood as the dominant form of matter in the universe. His tragedy was not that he was wrong, it was that he was right, repeatedly, decades early, and almost no one was willing to hear it from him. The confirmation he never received came, much later, from instruments he could not have imagined. When NASA launched the Chandra X-ray Observatory in 1999, one of its early targets was the Coma cluster. An X-ray telescope can see something an ordinary telescope cannot: the thin, scorching gas that fills the vast spaces between the galaxies in a cluster, heated by the cluster's gravity to tens of millions of degrees. That gas glows in X-rays, and from the way it glows, astronomers can calculate the gravitational field holding it in place. The mass that calculation demands is the same mass Zwicky inferred from the moving galaxies. It is worth appreciating what that hot gas tells us, because it is a third, independent way of weighing a cluster, on top of the moving galaxies and the bending of light. The gas is held in the cluster by gravity, the same as the galaxies are, but it gives itself away differently. If the cluster held only the mass of its visible stars, the gas would not be nearly so hot, nor packed so densely toward the center. It would have drifted away long ago. The very fact that the gas is there, glowing at tens of millions of degrees, trapped in the cluster's grip, tells you how deep that gravitational grip must be. And the answer, again, is far deeper than the stars alone could dig. 3 separate methods, the galaxy speeds, the lensing of background light, and the temperature of the trapped gas, all interrogate the same cluster in completely different ways, and all 3 return the same verdict. The cluster is far heavier than it looks. The X-ray data revealed that this hot gas actually outweighs all the stars in all the cluster's galaxies by something like a factor of 10. And quote, "It is ordinary matter, made of protons and neutrons, part of the 4.9%, and Zwicky had not known it was there. Its discovery softened his factor of 400 considerably, but even after counting every last atom of that hot gas, the majority of the cluster's mass was still missing. The modern figure is that about 85% of the Coma cluster is dark. Working with a small telescope and 8 galaxies, Zwicky had glimpsed the largest single fact about the contents of the universe, and had been told, in effect, to keep it to himself. The same imbalance appears in every massive cluster we have studied since. The stars, the galaxies, the hot gas, everything that gives off light adds up to perhaps 15 or 20% of the total. The rest is dark. Clusters are the largest gravitationally bound objects in existence, and they are, overwhelmingly, made of something we cannot see. But a cluster is a complicated, crowded thing, full of moving parts. For decades, it remained possible to wonder whether the missing mass was some artifact of that complexity, a misunderstanding of the dynamics, an overestimate of the speeds. To know whether dark matter was a universal feature of the cosmos, and not just a quirk of clusters, astronomers needed something simpler. They needed to look inside a single galaxy, and the answer, when it came, would come from a spectrograph pointed at the nearest large spiral to our own, and from a woman who had spent her entire career fighting for the right to point it. The first person to notice something strange in the rotation of a galaxy was not Vera Rubin. It was a graduate student at the University of California named Horace Babcock. In 1939, for his doctoral thesis, Babcock measured how fast different parts of the Andromeda galaxy were rotating. He found that the outer regions were moving far faster than they should have if the galaxy's mass were concentrated where its light was. It was a genuinely puzzling result, but Babcock and his advisors set it aside, attributing it to light being absorbed by dust and gas within the galaxy, dimming the outer stars and confusing the measurement. The thought that the galaxy might be wrapped in a vast halo of invisible mass was not seriously entertained. The result was filed away, and for more than 30 years, almost no one returned to it. The story resumed in the late 1960s at the Carnegie Institution in Washington. There, an astronomer named Vera Rubin was deliberately looking for a quiet research program, one that would keep her away from the loud and contentious arguments raging at the time about quasars and the expanding universe. She chose galaxies. She wanted to understand, in detail, how they turn. Rubin was no stranger to having to fight for the work. She was born Vera Cooper in Philadelphia in 1928, and she fell in love with the night sky as a child, lying awake watching the stars wheel past her bedroom window. When the time came to apply to graduate school, she wrote to Princeton and was told that women were not admitted to the astronomy program. They would not be for another quarter of a century. She went to Cornell instead, where she studied under some of the great physicists of the age, and then to Georgetown for her doctorate. Her thesis, on the way galaxies clump together across the sky, was decades ahead of its time, and was met largely with indifference, and in some quarters with hostility. The fight followed her to Palomar Observatory, the premier optical telescope in the United States, run by Caltech. For years, women were not formally allowed to observe there. The reason given was that the quarters were shared, and there were no separate facilities for women. When Rubin finally gained access in the mid-1960s, becoming the first woman officially permitted to observe at Palomar, she walked to the men's restroom door, which carried a little stick figure of a man, cut a small paper skirt, and taped it onto the figure. There. Now it was a women's room. She was not staging a protest. She simply needed somewhere to go. She told that story, in later years, with a dry humour and without bitterness, as one of many small obstacles she had simply walked around in order to keep doing the work. There had been others. She had been told, as a young woman, that she should consider studying something other than astronomy. She had been the only woman in rooms full of men for most of her career. She had published findings that were ignored and waited, sometimes for decades, to be proven right. Through all of it, her response was consistent. She did not argue about whether she belonged. She gathered data carefully and let it speak, and trusted that good measurements would eventually outlast bad assumptions. It is worth holding on to that, because the discovery she is about to make was not the work of a moment of genius. It was the work of someone who had learned, the hard way, to keep observing when the world was not paying attention. At Carnegie, Rubin began working with an instrument builder named Kent Ford, who had developed an image tube spectrograph of unusual sensitivity. The device could gather spectra from objects far too faint for earlier instruments, which meant it could measure the motion of stars and gas out at the dim, distant edges of galaxies, where the light grows thin and the signal weak. Together, Rubin and Ford set out to do something methodical and unglamorous. They would measure the rotation curves of spiral galaxies, the orbital speed of the stars and gas as you move outward from the center. Everyone knew, more or less, what they would find. The expectation came straight from the solar system. The planets close to the Sun move quickly, because they sit deep in the Sun's gravity. Mercury races around at about 48 kilometers per second. The Earth, farther out, moves at about 30. Neptune, far out at the edge, crawls along at about 5. The pattern is clear, and it follows from a simple fact that nearly all the mass of the solar system sits in the Sun at the center. The farther you go from the mass, the weaker the pull and the slower the orbit. A spiral galaxy looks, at first glance, like it should behave the same way. Its light is concentrated in the bright central bulge, where the old stars crowd together. Out in the disk, the starlight fades, and by the visible edge the galaxy is dim and diffuse. So the rotation curve should rise near the center, peak, and then fall away toward the edge, the speeds dropping as you move out past most of the mass. The only real question was how steeply that decline would go. Rubin and Ford began with Andromeda. They took spectra point after point across the galaxy's disk, measuring how the light was shifted by motion. The color stretched slightly redder where the stars moved away and squeezed slightly bluer where they moved toward us. From those shifts, they could reconstruct the speed at every radius. The work was painstaking, and it was done in the cold and the dark at the top of a mountain, one measurement at a time. To capture the spectrum of a faint patch of a galaxy, the telescope had to be held exactly on target for long stretches while the dim light trickled in, and Rubin spent many nights doing exactly that, guiding the instrument by hand, watching the faint smudge of Andromeda, recording the shift of its light point by point along the disk. There was nothing dramatic about the doing of it. It was the slow, careful accumulation of a curve, one dot at a time, the kind of patient observational work that rarely makes anyone famous. The drama was only in what the dots, when finally laid side by side, turned out to say. The curve did not decline. Near the center, the speed climbed quickly as expected, but then, instead of peaking and falling, it flattened and it stayed flat. Stars out at the visible edge of Andromeda were moving just as fast as stars far closer in. The galaxy was turning more like a solid wheel than like a system ruled by the falling pull of a central mass. Rubin and Ford checked the data for errors. They recalibrated the instrument. They took the measurements again. The flat curve held. They published the Andromeda result in 1970, cautiously, describing the flat curve without yet pressing its full meaning. Then they widened the survey. Galaxy after galaxy, dozens of spirals, large and small, near and far. Every single one told the same story. The rotation curves were flat, all the way out to the limit of what the instrument could reach. Where the light ended, the mass did not. The confirmation came from another direction at the same time, and it mattered because it removed any suspicion that the optical measurements were being fooled by dust. Radio astronomers, chief among them Morton Roberts, were tracing the rotation of galaxies using the radio emission of cold hydrogen gas, which extends far beyond the visible stars, out into the dark. The radio curves reached even farther than the optical ones, and they were flat too, flat well past the edge of anything that glowed. In 1978, a Dutch astronomer named Albert Bosma assembled radio rotation curves for 24 galaxies in his doctoral thesis, and the pattern was undeniable across the whole sample. The flatness was real, it was universal, and it ran out into regions where there was no visible matter at all. In 1980, Rubin and Ford, with their colleague Norbert Thonard, published the survey that settled it. Rotation curves for 21 spiral galaxies, every one of them flat. The conclusion could no longer be avoided. The mass of a galaxy is not concentrated where its light is. It is spread through a vast, roughly spherical halo that reaches perhaps 10 times farther than the visible disk and weighs perhaps 10 times as much as all the stars and gas combined. And because that halo gives off no light, it has to be made of something that does not touch light at all. There is a deep clue hidden in the shape of that halo, and it is worth drawing out. The visible part of a spiral galaxy is a thin, flat disk, a great spinning plate of stars and gas. The dark matter, by contrast, fills a fat, round, ball-shaped region enveloping the whole thing. Why the difference? The answer reveals something fundamental about what dark matter can and cannot do. Ordinary matter, when it falls together under gravity, collides with itself. The gas clouds crash, they heat up, and crucially, they can shed that heat by radiating it away as light. Losing energy, they sink, settle, and flatten into a spinning disk, the natural shape for matter that can cool. But dark matter cannot do this. It does not collide with itself, and it cannot radiate, because it does not touch light at all. It has no way to shed energy and sink, so it stays where gravity first gathered it, puffed up in a great sphere, unable to cool, unable to flatten, unable to form a disk or a star or a planet. This is why dark matter builds the scaffolding, but never the rooms. It can pull things together, but it can never settle down. Everything intricate in the universe, every star and world and living thing, is made of the minority substance, precisely because the minority substance is the one that can cool and collapse and become complicated. This was Zwicky's missing mass, found again now inside individual galaxies, on a scale 1,000 times smaller than the Coma cluster. The problem was not a quirk of crowded clusters. It was a property of galaxies themselves, of the one we live in as much as any other. Rubin later said it was the great surprise of her career. No one had predicted flat rotation curves. No theory had called for them. She and Ford had gone looking for the gentle Keplerian decline that everyone expected, and had simply not found it, anywhere they looked. It was not the first time Rubin had handed the field a result it did not want. Years earlier, she and Ford had measured the motions of galaxies across large stretches of sky and reported what looked like a large-scale streaming, whole groups of galaxies drifting together in a way the standard picture did not predict. The claim became known as the Rubin-Ford effect, and it was attacked, doubted, and largely set aside, though later work on the genuine large-scale flows of galaxies suggested she had again been pointing at something real before the tools existed to confirm it. She had, by this point in her life, developed a particular relationship with being disbelieved. She had learned to choose her battles, to gather data so carefully that it could not easily be waved away, and to let the measurements argue on her behalf. The rotation curves were chosen, in part, precisely because they were hard to dismiss. The evidence was simply too clean. In her later years, Rubin became one of the most quietly influential figures in American astronomy, not only for the discovery, but for her steady insistence that the field open its doors. She mentored younger women, pressed institutions to admit them, and pushed, with characteristic patience, against the exclusions she had spent her own career working around. She never received the Nobel Prize, an omission many of her colleagues considered a genuine failure of the award, and she seemed to mind less than they did, more interested in the next measurement than in the recognition for the last one. The theorists caught up quickly. As early as 1973 and 1974, Jeremiah Oestreicher and Jim Peebles at Princeton, working partly from the mathematics of how galactic disks hold their shape, had argued that a spiral galaxy needs a massive surrounding halo simply to remain stable, rather than tearing itself apart. When their argument met Rubin's measurements and Roberts's radio curves and Zwicky's old cluster, the separate threads pulled into a single rope. The conversation in astronomy shifted, almost audibly, from a question about whether dark matter was real to a question about what, in the world, it could possibly be made of. By the early 1980s, the dark halo had become a standard part of how galaxies were understood. The old picture of a galaxy as a self-contained island of stars whose mass followed its light was gone. In its place was something stranger and, in a way, more honest. Every bright galaxy was now understood to sit at the centre of a vast, invisible sphere of mass, a sphere whose nature no one could name. And the next clue to that nature would come not from the galaxies themselves, but from the oldest light in the universe. To weigh the universe as a whole, rather than galaxy by galaxy, astronomers turned to a source that, at first, seems to have nothing to do with dark matter. It is the faint afterglow of the Big Bang itself, a sea of radiation that fills all of space, and which we can read like the page of a ledger. The story of that radiation begins with an accident. In 1965, two engineers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were trying to calibrate a large horn-shaped antenna and could not get rid of a faint, steady hiss of microwave noise. It came from every direction in the sky, day and night, in every season. They checked the antenna for faults. They evicted a pair of pigeons that had nested inside it and scrubbed out what the birds had left behind. The hiss remained. What they had found, it turned out, was the cosmic microwave background, the light released when the universe was young, predicted years earlier by theorists who had reasoned that the early cosmos must have been hot and dense. Penzias and Wilson had stumbled onto the edge of creation while trying to clean up their signal, and the discovery would later earn them the Nobel Prize. Here is what that light is. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma of protons, electrons, and photons, all crowded together. It was opaque. Light could not travel far before it scattered off a free electron and changed direction, the way a beam cannot pass cleanly through fog. But the universe was expanding, and as it expanded it cooled, and after about 380,000 years it crossed a threshold. It grew cool enough for the protons and electrons to combine into neutral hydrogen atoms. Suddenly there were no more free electrons to scatter the light. The fog lifted. The photons, released all at once, streamed out across the cosmos, and they have been travelling ever since, stretched by the universe's expansion from visible light into the faint microwaves we detect today. The light we catch now left on its journey when the universe was less than 1,000th of its present age, when there were no stars, no galaxies, no planets, nothing but the cooling haze and the gathering dark matter within it. Every patch of that light has been travelling toward us, unobstructed, for more than 13 billion years, and the particular patch we collect tonight set out from a shell of the early universe that happens to lie 13 billion light-years away in every direction. It is, in a real sense, the most distant thing we can ever see, and the oldest. There is no light from before it, because before it, the universe was opaque. The background radiation is a wall, the surface of the fog, and we are looking at the moment the cosmos became clear. Everything we know about the era before the first stars, including almost everything we know about dark matter's role in building the universe, is read from the faint pattern printed on that wall. That ancient light is almost perfectly smooth, the same temperature in every direction to a few parts in 100,000. But not quite. Embedded in it are tiny variations, faint patches very slightly warmer or cooler than the average, and those variations are a map of the lumps and ripples in the early universe, the places where matter was slightly more or slightly less concentrated. The pattern of those ripples is not random. It carries the imprint of sound waves that rolled through the primordial plasma before the fog lifted, pressure waves whose size and spacing depend, exactly and calculably, on what the universe was made of. It is worth dwelling on that phrase, sound waves, because it is meant literally, not as a figure of speech. Before the fog lifted, the universe was a single connected fluid of matter and light, and like any fluid, it could carry pressure waves, which is to say, sound. Regions where gravity pulled matter inward would heat and push back outward through the pressure of the trapped light, then fall inward again, a slow cosmic ringing. The early universe was, in a real sense, filled with sound, a deep tone far too low for any ear, a note, dozens of octaves below the lowest a piano can play. When the fog lifted and the light escaped, that ringing was frozen into the pattern of warm and cool patches, and when we measure the characteristic size of those patches today, we are reading the wavelength of the longest-lived note the universe ever sang. The whole edifice of precision cosmology rests, in the end, on measuring the pitch of that primordial sound. that there should be any afterglow at all was predicted before it was found. In the late 1940s, the physicist George Gamow and his younger colleagues, Ralph Alpher and Robert Herman, reasoned that if the universe began hot and dense, it should have left behind a faint bath of radiation, cooled by the long expansion to just a few degrees above absolute zero. Their prediction was largely forgotten, and Penzias and Wilson, evicting their pigeons in 1965, had not even heard of it. The match between the forgotten prediction and the accidental discovery, once people realized what had happened, was one of the moments that turned the Big Bang from one idea among several into the settled framework it is today. This is where the precision comes from, and 3 generations of spacecraft have sharpened it. NASA's COBE satellite, launched in 1989, first detected the tiny temperature ripples and confirmed that the background light had the precise spectrum the theory demanded, work that won its leaders the Nobel Prize. NASA's Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped the ripples in far finer detail and began turning them into hard numbers about the contents of the cosmos. And the European Space Agency's Planck satellite, which observed from 2009 to 2013, produced the definitive map, the sharpest image of the infant universe we possess. Each of these missions was an act of enormous patience and care. The signal they were chasing is faint almost beyond imagining, a glow only a few degrees above absolute zero, with the meaningful variations 100,000 times fainter still. To see it, the instruments had to be chilled to extraordinary cold and flown far from the warmth and radio chatter of the Earth, some of them to a quiet point well beyond the Moon's orbit where they could stare at the sky undisturbed for years. They scanned the whole heavens, again and again, building up the faint pattern through sheer accumulation, averaging away the noise until the ancient ripples emerged. The final map from the last of these missions is one of the most information-dense images ever made. A single picture of the entire sky, as it looked 13.8 billion years ago, and folded into its pattern of warm and cool patches, is the recipe of the universe. The proportions of ordinary matter, and dark energy read off to a precision that would have seemed like fantasy a generation earlier. The way the numbers come out is this. The pattern of ripples, when you analyze it carefully, shows a series of peaks, like the overtones of a struck bell. The first and largest peak tells you the overall geometry of the universe, and it says space is flat, which fixes the total amount of mass and energy. The second peak, measured against the first, tells you how much ordinary matter there is, the protons and neutrons. And the third peak is sensitive to the dark matter, because dark matter and ordinary matter responded differently to those primordial sound waves, and that difference is written into the heights of the peaks. From the relative heights, the Planck team could read off the recipe directly. The total matter density of the universe comes out at about 31% of the so-called critical density, the amount needed to make space flat. The ordinary matter, the baryons, comes out at about 4.9%. The difference, around 26%, is the dark matter. It is about 5 times the ordinary matter, exactly as the galaxies and clusters had been suggesting for decades, now confirmed by a completely independent measurement made from light that has been crossing the universe for 13.8 billion years. And there is a second, separate confirmation of the ordinary matter figure, which makes the whole thing harder to argue with. In the first few minutes after the Big Bang, before any stars existed, the universe was hot enough to fuse the lightest elements, hydrogen into helium, with traces of deuterium and lithium. The exact proportions that came out of that early furnace depend, very sensitively, on how many protons and neutrons were packed into each volume of space. Deuterium, in particular, a heavy form of hydrogen, is a delicate gauge of the density. When astronomers measure how much deuterium survives in the most pristine, untouched gas clouds in the distant universe, they get a baryon density that matches the figure from the background light, almost exactly. 2 entirely different windows onto the early universe. The light from one era and the chemistry from another agree on how much ordinary matter exists, and both agree it is only a small slice of the whole. That agreement is one of the quiet triumphs of 20th century physics, and it is worth pausing on, because it is the kind of thing that gives scientists confidence in the whole framework. The theory that describes those first few minutes was worked out decades ago, and it makes specific, unforgiving predictions about the abundances of the lightest elements. For helium and deuterium, the predictions hit the measurements almost perfectly. There is one lingering wrinkle, the so-called lithium problem, where the predicted amount of one form of lithium comes out about 3 times higher than what we actually observe in the oldest stars. A discrepancy still not fully resolved, and a reminder that even the well-tested parts of cosmology keep a few loose threads. But on the central question, the amount of ordinary matter, the early chemistry, and the ancient light shake hands. The conclusion they reach together is not in serious doubt. The atoms are a minority, and a small one. So when we weigh the universe with the oldest and most complete data we have, we find that the atoms we are made of are barely a trace component. Everything you can see, everything you have ever touched, everything anyone has ever built or loved or buried, is made of the exception, not the rule. The Sun, which holds more than 99% of the mass of our entire solar system, is itself made of ordinary matter, and ordinary matter is a rounding error in the accounts of the cosmos. The Milky Way, with its 200 billion stars and its great glowing arms, is a thin layer of frost on the surface of something far larger and entirely invisible. The numbers do not lean on any exotic theory. The background light gives the total matter. The early chemistry and the background light together give the ordinary matter. The difference is dark matter, and the same ratio of roughly 5:1 keeps reappearing. In clusters, in single galaxies, in the rotation of gas, in the oldest light. That consistency, across methods that have nothing to do with one another, is what convinced cosmologists that dark matter is not a mistake in the equations. It is a substance. It is there. The remaining problem, which has now consumed 40 years of effort, is to say what it is. But before that, there is a deeper thing the background light reveals, something stranger than the abundance. It reveals that without dark matter, there would be no galaxies for it to hide inside, no stars, no planets, and no one in the dark to ask the question at all. To see why, you have to go back to the hot plasma of the early universe, before the fog lifted, and ask a question that troubled cosmologists for years. The universe today is full of structure, galaxies, clusters, immense filaments of matter stretched across hundreds of millions of light years. All of that grew, under gravity, from the tiny ripples we can still read in the background light. But there is a problem with that story, and the problem is timing. In that early plasma, ordinary matter was locked together with the radiation. The photons pressed against the protons and electrons constantly, and that pressure pushed outward. Any clump of ordinary matter that tried to collapse under its own gravity was immediately shoved apart again by the radiation, like a wave flattening a sandcastle before it can rise. This went on for the entire opaque era, nearly 400,000 years. During all that time, ordinary matter was effectively held in place. It could not gather. It could not build anything. You can picture it as a tug-of-war that lasted 400,000 years. On one side, gravity, patiently trying to pull every slight overdensity of matter into a tighter knot. On the other, the pressure of the trapped light, shoving back out every time the matter tried to fall inward, so that instead of collapsing, the ordinary matter could only oscillate, in and out, the cosmic ringing we met before. Neither side could win while the fog held. Gravity could not build, because the light would not let it. The light could not disperse the matter entirely, because gravity kept pulling it back. So the ordinary matter was trapped in place, sloshing, unable to make anything permanent, for the whole length of the opaque era. And that is the problem, because the universe we live in is full of permanent things, and there was not enough time after the fog lifted to build them all from a standing start. And yet, when the fog lifted, structure formed astonishingly fast. Galaxies were already assembling within a few 100 million years. There simply was not enough time, after the radiation released its grip, for ordinary matter to start from those faint ripples and grow all the way up to galaxies. The arithmetic does not work. Something must have gone ahead of the ordinary matter. Something must have started gathering long before the fog lifted, building deep gravitational wells, so that when the ordinary matter was finally freed, it had somewhere to fall. That something was dark matter, and the reason it could go first is the same reason we cannot see it. Dark matter does not feel the radiation. Photons pass straight through it. It was never locked to the plasma, never shoved apart by the pressure of the light. So while the ordinary matter was held frozen for 400,000 years, the dark matter was free, all that time, to do what gravity wants to do, to gather, to deepen, to concentrate. The faint ripples grew, in the dark matter, into a network of valleys and basins, a vast scaffolding of dense regions and connecting filaments already in place when the universe became transparent. This is the quiet resolution of the timing problem, and it is one of the strongest arguments that dark matter is a real substance rather than a trick of gravity. The numbers genuinely do not work without it. If the only matter in the universe were the ordinary kind, held frozen by the radiation until the fog lifted, then everything would have had to grow from those faint ripples in the time since. And there simply has not been enough of that time. The galaxies we see in the young universe, already formed and shining when the cosmos was a fraction of its present age, could not exist. They would still be forming now, or not yet formed at all. The only way to account for a universe this richly structured, this early, is to have something that began gathering long before the ordinary matter was released, digging the wells in advance. That something cannot interact with light, or it would have been frozen along with everything else. It must be dark. The very existence of galaxies, on the schedule we observe, is an argument for dark matter, as forceful as any measurement of any single galaxy's spin. Then the fog lifted, and the ordinary matter was suddenly free, and it felt that hidden landscape for the first time without the radiation pushing back. And it fell. It poured into the dark matter's valleys, pooling in the deepest basins, cooling and condensing until it caught fire as the first stars. The galaxies lit up at the nodes of a structure that was already there. The luminous universe is not scattered at random. It is a tracing, in light, of an older and invisible architecture. Every galaxy, every cluster, every bright filament marks a place where dark matter had already gathered and was waiting. Try for a moment to stand inside that early universe, before any of it was lit. There are no stars yet. There is no light to see by, because the light itself is still trapped in the fog, scattering endlessly off the trapped matter. Everything is a uniform, glowing warmth, almost perfectly smooth in every direction, and within it, silent and invisible, the dark matter is already moving, already drawing itself together along faint seams, deepening the valleys that the galaxies will one day fall into. Nothing about this scene announces what is coming. There is no spiral, no disk, no point of light anywhere. There is only a featureless warm haze and, threaded through it, a gathering darkness that will become the skeleton of everything. You could not have looked at that early universe and guessed at galaxies. The blueprint was there, but it was written in a substance that gives off nothing and would not be read for billions of years. This is not a comfortable just-so story told because it sounds good. It follows from the physics, and it has been tested directly by trying to build the universe inside a computer. In the mid-1980s, a group of 4 physicists, Mark Davis, George Efstathiou, Carlos Frenk, and Simon White, sometimes called the Gang of 4, ran some of the first serious simulations of how cosmic structure grows if it is governed by dark matter. And they found that one crucial detail mattered enormously: the speed of the dark matter particles in the early universe. If the dark matter were light and fast-moving, what physicists call hot, it would have streamed across great distances before it could settle, smearing out the small ripples and erasing the seeds of small structures. A universe like that would build the largest things first, immense sheets and superclusters, which would then have to fragment into galaxies. But that is not the universe we see. We see the opposite order. Small things, dwarf galaxies and modest galaxies, formed early and then merged and gathered into larger and larger systems over time, from the bottom up. For that to happen, the dark matter has to be slow and heavy, what physicists call cold. The simulations of cold dark matter reproduce the observed universe. The simulations of hot dark matter did not. And so the early candidate that many had hoped for, the lightweight neutrino, was set aside as the main ingredient. Whatever dark matter is, it is mostly cold. There is a possibility in between, and it has not gone away. Dark matter could be warm, made of particles lighter and faster than the cold case, but heavier and slower than a neutrino, just energetic enough to smooth out the very smallest structures while leaving the large ones intact. Such warm dark matter would soften some of the small-scale problems the simulations run into, And one candidate for it, a heavier and shyer cousin of the ordinary neutrino called the sterile neutrino, has become a quiet focus of interest. We will return to it, because for a brief stretch a real and unexplained signal seemed to point its way. The most extreme proof that dark matter dominates comes from the smallest galaxies of all. Scattered around the Milky Way are dim, sparse little galaxies called dwarf spheroidals, some of them containing only a few thousand stars, faint enough that several were not even discovered until recent decades. When astronomers measure how fast the handful of stars in one of these dwarfs are moving, the speeds are far too high for the visible stars to hold the system together. These little galaxies should have flown apart long ago, unless they are held by an overwhelming amount of unseen mass. In some of them, the dark matter outweighs the visible stars not by a factor of 5, but by a factor of 100 or more. They are, in effect, clumps of dark matter with a faint dusting of stars on top, the purest examples of the substance we have, and the best natural laboratories for studying it, which is why the indirect searches so often point their telescopes at exactly these dim and unremarkable-looking objects. A dwarf galaxy is quiet, with few of the ordinary processes that produce gamma rays in busier places, so if a faint glow of annihilating dark matter exists anywhere we could hope to catch it, one of these dense, starved little galaxies is where it should stand out most clearly against the dark. So far, those searches have seen nothing, but they have looked harder there than almost anywhere, precisely because the dark matter is so concentrated and so undisturbed. The most ambitious of these simulations came 2 decades later. In 2005, an international group called the Virgo Consortium ran what they named the Millennium Simulation. They took a representative cube of the early universe, filled it with 10 billion particles standing in for dark matter, set the initial ripples to match what the background light had measured, and let gravity run for the equivalent of 14 billion years. Out of those 10 billion points, a structure grew, a vast web of filaments and dense knots wrapped around enormous empty voids, the largest knots heavy enough to host clusters of galaxies, the filaments strung with smaller knots where individual galaxies would form. When the simulated web was laid beside real maps of where galaxies actually sit in the sky, drawn from surveys that catalogued millions of real galaxies, the two matched, in their statistical shape, knot for knot and void for void. The galaxies in the real universe are not placed at random. They trace the web, and the web is dark matter. The scale of that web is hard to hold in the mind. The filaments of the cosmic web stretch for hundreds of millions of light years, threads of dark matter strung with galaxies like beads of dew on a spider's web. Between the filaments lie the voids, vast and almost perfectly empty regions, some of them hundreds of millions of light years across, containing almost no galaxies at all. If you could pull back far enough to see the whole observable universe at once, it would not look like a smooth scattering of galaxies. It would look like foam, or like a sponge, or like the branching network of cells in living tissue, a structure of walls and filaments and great hollow bubbles, all of it shaped by the gravity of the dark matter that gathered first. The largest single structures in the universe, the great walls and superclusters that span 1 billion light years, are features of that web. And the web is not made of the things that shine. It is made of the things we cannot see, with the shining things merely caught in it, lit up at the densest knots, like frost gathering on the coldest threads. We have even begun to map the dark matter wrapped around our own galaxy from the inside. The European Space Agency's Gaia spacecraft has spent more than a decade measuring the precise positions and motions of more than 1 billion stars in the Milky Way, building the most detailed 3-dimensional map of our galaxy ever made. From the way those stars move, astronomers can weigh the invisible halo they are embedded in, trace the long streams of stars torn from smaller galaxies the Milky Way has swallowed, and even find evidence of an ancient collision billions of years ago, when our galaxy merged with another and absorbed its dark matter along with its stars. The halo, it turns out, is not perfectly smooth. It is lumpy, wrinkled, scarred by old mergers, a record of the galaxy's violent history written in the motions of stars that have long since forgotten it. So the carbon in your cells, the oxygen filling your lungs as you breathe slowly in the dark, the calcium in your bones, the iron carried in your blood, every one of those atoms was forged inside a star, and every one of those stars ignited inside a well of dark matter that had been dug long before the first sunrise anywhere in the cosmos. You are not simply living in a universe that happens to contain this invisible substance. You are living in a universe that was built around it, and you are made of the material that arrived afterward and settled into the spaces it had already prepared. The simulations did get some things not quite right, and the places where they disagree with reality are interesting rather than embarrassing, because they may be telling us something about the precise nature of the dark matter particle. The cold dark matter models predict that each large galaxy should be surrounded by a great swarm of small satellite galaxies, more than we actually count around the Milky Way. They predict that the centers of galaxies should have sharp, dense spikes of dark matter, where many real galaxies seem to have gentler, flatter cores. These tensions have names: the missing satellites problem, the cusp core problem, and we will return to them, because honest science keeps a list of where its best theory still strains. But on the large scale, from the size of a galaxy up to the size of the whole observable universe, the dark matter picture works. It built the cosmic web. It explains the background light. It explains how galaxies formed in the time available. The next question was unavoidable. If this substance is real, and cold, and built everything, then it is made of some kind of particle. What particle? And could we catch one? The first serious answer came out of particle physics, and for a while it looked almost too good to be true. In the late 1970s and early 80s, physicists trying to extend their theory of the known particles kept producing, almost as a side effect, a new kind of particle that was heavy, electrically neutral, and interacted only very weakly with everything else. Such a particle came to be called a WIMP, short for weakly interacting massive particle, and it had a property so neat that physicists named it the WIMP miracle. Here is the miracle. In the first instance after the Big Bang, when the universe was unimaginably hot, every kind of particle was being created and destroyed constantly, in balance. As the universe expanded and cooled, it eventually became too cool to create the heavy WIMPs any longer, and they began to disappear, annihilating in pairs when they met. But the universe was also thinning out as it expanded, and at some point the WIMPs became so spread out that they could no longer find each other to annihilate. Their number froze. A leftover population was locked in, a relic of the first fraction of a second, and it would drift through the universe ever after. The astonishing part is the arithmetic. The size of that leftover population depends on the particle's mass and on how strongly it interacts. And if you plug in a mass of roughly 100 to 1,000 times the mass of a proton, and an interaction strength typical of the weak nuclear force, the leftover amount comes out almost exactly equal to the amount of dark matter that astronomers had measured in the sky, by completely separate means. The particle physicists had not been trying to solve the dark matter problem. They had been trying to fix unrelated puzzles in their own theory. And out of that effort fell a particle that, all on its own, would naturally leave behind the right amount of dark matter. Cosmology and particle physics, for one beautiful stretch of years, seemed to be pointing at the same answer. To feel why this caught people's imagination, hold the two numbers side by side. On one side, the amount of dark matter in the universe, a figure measured by astronomers from the spin of galaxies, the motion of clusters, the pattern in the ancient light, a number rooted entirely in the heavens. On the other side, the leftover abundance of a hypothetical particle calculated entirely from the physics of the very early universe, from how fast a heavy, weakly interacting particle would have stopped annihilating as the cosmos thinned out, a number rooted entirely in the laws of the small. These two numbers come from completely different worlds, the astronomical and the subatomic, with no obvious reason to be related, and when you work them out, they very nearly match. A particle weighing a few hundred times a proton, interacting through the weak force, would leave behind just about the measured amount of dark matter. That near coincidence that two such distant calculations should land on the same figure looked less like an accident and more like a clue, a place where two halves of physics seem to be touching. It is the single most important reason the WIMP dominated the search for so long, and the slow fading of it, as the detectors found nothing, has been one of the quieter disappointments in modern science. The favourite candidate had a name, the neutralino. It comes from a proposed extension of physics called supersymmetry, which suggests that every known particle has a heavier undiscovered partner. In many versions of that theory, the lightest of these partners is the neutralino, and it has exactly the properties dark matter needs. It is stable because there is nothing lighter for it to decay into. It is electrically neutral, so it does not touch light. It interacts only through the weak force and through gravity. For more than 2 decades, the neutralino was the overwhelming favorite, the particle most physicists expected to find. The whole field organized itself around the hunt. The appeal ran deeper than convenience. Supersymmetry was not invented to explain dark matter at all. It was proposed to solve other, more technical problems, to stabilize the mathematics of the known particles, to hint at how the forces of nature might unify at very high energy. The dark matter candidate emerged from it as an unplanned bonus, a particle that nobody had set out to create, but that arrived with precisely the right weight, the right shyness, and the right stability. When a theory built for one purpose throws off a solution to an entirely separate problem, physicists take that as a sign they may be on the right track. For a generation, supersymmetry and the WIMP looked like one of those beautiful convergences where several deep problems dissolve together, and the confidence it inspired is part of why its absence has been felt so keenly. And there were 3 ways to hunt. You could try to make the particle yourself, by smashing ordinary matter together at enormous energy and watching for the telltale gap where a dark matter particle had carried energy away unseen. You could look for the particle out in space, by hunting for the faint debris, the gamma rays and other particles, produced when 2 of them collide and annihilate somewhere in the galaxy. Or you could wait for one to come to you by building a detector so quiet and so sensitive that it could register the tiny nudge of a single dark matter particle, striking a single atomic nucleus as it drifted through. All 3 hunts have been pursued for more than 40 years at vast expense and with remarkable cleverness, and none of them has produced a confirmed catch. There is a pleasing logic to the 3 approaches, because they are really the same interaction read in 3 directions. If a dark matter particle and an ordinary particle can touch at all, however faintly, then that single fact has 3 consequences. Run the interaction forward, and ordinary particles smashed together hard enough can make dark matter, which is the collider. Run it in reverse, and 2 dark matter particles meeting can turn into ordinary particles, which is the search in space for the debris of their annihilation. And run it sideways, and a dark matter particle passing through ordinary matter can occasionally bump into it, which is the detector waiting underground. The same faint doorway between the dark world and ours, approached from 3 sides. If the doorway exists at all, at least one of the 3 should eventually find it. That all 3 have come up empty, after 4 decades, is either a sign that the doorway is even smaller than anyone hoped, or a sign that the particle we imagined on the other side of it is simply not there. Consider the first approach, the colliders. If WIMPs exist, then slamming ordinary particles together hard enough should, now and then, conjure a pair of them into being. They would slip out of the detector unseen, but their absence would show up as missing energy, an unbalanced collision. The Large Electron-Positron Collider at CERN ran throughout the 1990s looking for signs of supersymmetry, and found none. The Tevatron at Fermilab in Illinois searched through the same years and found none. And the Large Hadron Collider, the most powerful machine ever built for this purpose, has been colliding protons since 2008. It found the Higgs boson, the last missing piece of the older, established theory. It has not found a single trace of supersymmetry, nor any other particle that could be the dark matter. The simplest, most elegant versions of the theory predicted that something should already have appeared. Nothing has. It is hard to convey, from outside the field, how much weight had been placed on supersymmetry, and how quietly painful its absence has been. For 30 years it was the leading idea for what lies beyond the known particles, taught in textbooks, built into the expectations of a whole generation of physicists. It solved several deep puzzles at once, tidied up the mathematics, and threw in a perfect dark matter candidate almost for free. Many physicists were confident that when the Large Hadron Collider reached full power, the superpartners would come tumbling out. The collider reached full power. The superpartners did not come. They may still exist, at energies beyond the machine's reach, but the most natural versions, the ones that solved the puzzles most elegantly, are the ones now most firmly excluded. The dark matter candidate that fell out of the mathematics like a gift has not appeared where it was most expected to be. and the field has had to absorb that, slowly, the way one absorbs the loss of a long-held assumption. The second approach, the search out in space, has been almost as quiet, though with a few tantalizing ambiguities. NASA's Fermi Gamma Ray Space Telescope has surveyed the whole sky since 2008, and it sees an excess of gamma rays coming from the center of the Milky Way, more than the known sources seem to account for. For a while, this stirred real excitement, because annihilating dark matter would produce a glow of just that kind. But the center of the galaxy is crowded, and a population of rapidly spinning neutron stars known to emit gamma rays could produce a very similar signal, and the balance of opinion has slowly tilted toward that more ordinary explanation without fully closing the door. A particle detector mounted on the International Space Station has measured an unexpected excess of antimatter particles in the cosmic rays, which again could come from dark matter, and again could come from spinning neutron stars. And an enormous neutrino observatory buried in the ice at the South Pole has looked for neutrinos streaming out of the Sun, where dark matter might pile up and annihilate in the core, and has seen nothing above the expected background. Every promising hint has had a more boring twin that refuses to be ruled out. There was one more signal, briefly thrilling, that is worth telling because it shows how these things rise and fade. Around 2014, two separate teams, studying the X-rays pouring out of galaxy clusters and nearby galaxies, reported a faint emission line at a specific energy, a thin spike of X-ray light at a wavelength that did not match any known atomic transition. An unexplained line like that is exactly what you might expect if a dark matter particle were very slowly decaying, each decay releasing a photon of fixed energy. For a time, there was genuine hope that the line was the death glow of a sterile neutrino, the warm dark matter candidate, finally caught in the act. But other teams, looking at other objects, could not consistently reproduce it. Some saw it, some did not, and the places it should have appeared most strongly were not always the places it appeared at all. Like the gamma ray excess and the antimatter excess, it has settled into the long uncertain middle, neither confirmed nor quite killed, a faint line in old data that may be a clue or may be an instrumental ghost. Which leaves the third approach, the patient one, the one that has become almost a meditation. It is the attempt to catch a dark matter particle directly, here on Earth, as billions of them pass through every second. And to understand how that is even possible, it helps to go where the detectors are. You are 1,400 meters beneath a mountain. Above your head is the solid rock of the Apennines, in central Italy, more than a kilometer of it, and that rock is doing something specific. It is blocking the constant rain of cosmic ray particles that falls on the surface of the Earth, cutting their number by a factor of 1,000,000, so that down here the air is quiet in a way it never is in daylight. You are in a vast hall carved out of the stone, and at its center sits a tank, and inside the tank, kept colder than almost anywhere in nature, is a quantity of liquid xenon, a heavy, transparent, noble element that wants to react with nothing. The tank is wrapped in layer after layer of shielding, lead and copper and water, and lined with sensors that watch for the faintest flash of light. Almost nothing happens here. That is the entire point. The detector is built to register the single event, perhaps once in a year, when a dark matter particle drifting up from the galaxy strikes one xenon nucleus and makes it recoil, a flicker of light and a whisper of electric charge, pulled out of an emptiness so deep it took years of engineering to create. This is what the search has become, not a telescope pointed at the stars, a cathedral of silence, underground, waiting. The effort to build such places grew steadily over 4 decades. The first detectors, in the 1980s, were modest, small crystals of germanium or silicon chilled to extreme cold, set in shallow tunnels, watching for an excess of nudges they could not otherwise explain. They saw nothing that required dark matter. The second generation went deeper and grew heavier. The cryogenic dark matter search ran in a mine in Minnesota. A French experiment ran in a road tunnel beneath the Alps. Another ran in the same Italian hall beneath the Apennines, using crystals of a different material. None found a convincing signal, but each one tightened the limits, ruling out possibility after possibility. The engineering required to make these detectors quiet is its own quiet marvel. The enemy is radioactivity, which is everywhere, in the rock, in the air, in the very materials the detector is built from, each faint decay capable of mimicking the signal being hunted. So the builders go to extraordinary lengths. They use lead recovered from ancient sunken ships, because lead that has sat on the seafloor for centuries or millennia has had time for its own faint radioactivity to fade away. They use copper grown and machined underground, so that it is never exposed to the rain of cosmic rays at the surface that would make it faintly radioactive. They chill their detectors to within a fraction of a degree of absolute zero, the coldest temperature there is, so that the random jostling of heat itself does not drown the whisper they are listening for. Everything about the design is an exercise in subtraction, in removing source after source of noise, until what remains is a silence deep enough that a single particle from the galaxy could be heard arriving. Stand there again, in that silence. You are a kilometre and more beneath the mountain, and the detector is colder than deep space, and so still that the loudest thing in the chamber is the slow, patient electronics waiting for an event that may not come this year or next. Outside, on the surface, the world is loud with radiation, sunlight, cosmic rays, the faint glow of the rocks themselves. Down here, all of that has been stripped away, layer by deliberate layer, to make a pocket of the universe quiet enough to hear the dark. The physicists who tend these machines speak of them with a kind of tenderness. They have given years to building a perfect ear, and they will sit with it through the long night of the data, listening, while most of the people whose atoms drift through the same dark matter sleep soundly above, never knowing the listening is going on. The third generation scaled up to the ton, and much of it ran on liquid xenon, and much of that traces back to one physicist, Elena April, born in Milan, trained partly under one of the great experimentalists of the age. She went to Columbia University in New York and spent decades championing xenon as the ideal medium for this hunt, when it was far from obvious that it would work. The experiment she built grew step by step, from a 10-kilogram prototype to a 100-kilogram version, to a detector holding a full ton of liquid xenon beneath the Apennines, and then to the multi-ton instrument running there today. Each step pushed the sensitivity deeper. Each step found nothing, and turned that nothing into a sharper limit on what the particle could be. It is a particular kind of scientific life, to spend a career building ever more exquisite instruments to detect something that, so far, has declined to appear. April has spoken about that openly, about the discipline of it, about continuing to refine the question, even as the most hoped-for answer recedes. The limits these detectors have reached are difficult to picture. The interaction between a dark matter particle and ordinary matter, if it happens at all, is now known to be so faint that a single dark matter particle could pass through a wall of solid lead a light year thick and still, most likely sail clean through without touching a single nucleus. And the detectors have grown so sensitive that they are now beginning to bump against a new and unwelcome flaw. The sun, and other natural sources, produce a steady drizzle of ordinary neutrinos, and neutrinos, too, can nudge a nucleus in just the way a dark matter particle would. As the detectors improve, they are approaching the point where this neutrino fog becomes impossible to distinguish from the signal they are hunting. The current detectors, beneath the Apennines, in a former gold mine in South Dakota, called the Lux Zeppelin experiment, and beneath a mountain in China, are pushing toward that fog. As of now, after 40 years, the most hoped-for version of the WIMP has not been found, and the space left for it to hide in has shrunk dramatically. The miracle, which once felt like a near certainty, has come to feel more like a coincidence that did not hold. There is something worth sitting with in the shape of that result. The experiments have not failed. A detector that searches and finds nothing has still measured something real, namely that the particle, if it exists, must be even shyer than we thought, hiding in an even smaller corner of the possible. Each null result is a wall built, closing off a region of possibility, forcing the theorists to retreat to stranger and stranger ground. 40 years of patient searching has not caught the WIMP, but it has mapped, with great precision, all the places the WIMP is not, and that map is itself a hard-won piece of knowledge. It is just not the piece anyone wanted. The people who built these machines have spent their careers narrowing the darkness, and the darkness has narrowed, and the thing they were chasing has stayed inside it. Just ahead. Always just ahead. And yet, against all that silence, there is one detector that claims to hear something. For more than 20 years, in a hall next to the xenon experiments beneath the very same Italian mountain, an experiment called DAMA has reported a signal that will not go away. The signal has grown steadily stronger by the measures physicists use, far past the threshold that would normally count as a discovery, and almost no one in the field believes it is dark matter. To understand that strange standoff is to understand something about how science actually works, in the long stretches where the answer refuses to come. DAMA uses a different material from the xenon detectors, crystals of sodium iodide, which give off a tiny flash of light when a particle interacts inside them. The clever part is not the material but the method. The experiment does not try to catch a single unmistakable particle. Instead, it looks for a rhythm, an annual heartbeat, and the reasoning behind it is genuinely elegant. The Sun, carrying the whole solar system with it, is moving through the galaxy and therefore through the surrounding cloud of dark matter at about 220 kilometers per second. The Earth, meanwhile, orbits the Sunday. For half the year, the Earth's motion around the Sun adds to that great galactic drift, and for the other half it subtracts from it. So the speed at which the Earth plows through the dark matter should rise and fall once a year, peaking around June and dipping around December. If a detector is really catching dark matter, the rate of events inside it should swell and shrink with that same yearly rhythm. A small modulation, just a few percent, but a rhythm that ordinary backgrounds would find very hard to fake. The beauty of the method is that it does not require knowing exactly what a single dark matter event looks like, which is the hardest part of every other experiment. It only requires that whatever the detector is seeing should beat once a year, in step with the Earth's passage through the galactic wind, peaking and dipping on specific calendar dates fixed by orbital mechanics. Almost nothing else in a deep underground laboratory naturally keeps that exact schedule. A signal that rises in June and falls in December, year after year, locked to the Earth's motion through the halo, is hard to produce by accident. That is the strength of the claim, and it is why it has been so stubbornly hard to dismiss outright, even as it has been so stubbornly hard to confirm. The team behind DAMA, led for decades by the Italian physicist Rita Bernoulli, has watched their crystals for more than 20 annual cycles, and the rhythm is there. The events rise and fall once a year, peaking close to where the dark matter theory says they should. By the cold statistics of it, the signal is overwhelming. The problem is that no other experiment can find the same thing. The xenon detectors, the germanium detectors, all the others, looking for the very particles that should also be setting off the DAMA crystals, see nothing. In the simplest and most natural models of dark matter, a particle that would shake the sodium iodide crystals in Italy should also be shaking the xenon next door. It is not. For years, the field has been locked in an uncomfortable stalemate. The DAMA team has been criticized for not sharing its raw data in a form that would let outsiders check the analysis fully. Critics have proposed ordinary explanations for the yearly rhythm, things that also change with the seasons, temperature, or traces of radioactive gas, or subtle drifts in the equipment, even the slow seasonal breathing of the rock and air around the detector. None of those explanations has been conclusively proven either. The DAMA team has answered each objection in turn, insisting that their crystals are exceptionally pure, their environment exceptionally stable, and their rhythm exactly where the dark matter theory predicts. And there the matter sat, year after year, two communities of careful people unable to agree on what a single set of detectors was telling them. To break the deadlock, two new experiments were built specifically to copy DAMA's setup as closely as possible, using the same sodium iodide crystals, the same basic design, the same kind of deep underground shielding, one in an underground laboratory in South Korea, and one beneath the Pyrenees in Spain. The whole point was to remove every difference, except the question itself. If the rhythm came from dark matter, it should appear in the copies. If it came from something peculiar to DAMA's own crystals or its own surroundings, it should not. In the early 2020s, both experiments reported their first years of data. Neither saw the annual rhythm that DAMA sees. The measurements are not yet final, and the test continues, gathering more years to be sure, but the early weight of it presses hard against the original claim. It is a clean example of how science is meant to resolve such things, not by argument, but by building another instrument and asking the universe the same question again. It is worth pausing on the human shape of this. Rita Bernabe has given a large part of her working life to one experiment and one persistent result, and she has faced years of doubt, dismissal, and at times open hostility from colleagues convinced the signal is an artifact. She has continued to report exactly what her detectors record. Whether she is ultimately right or wrong, and the evidence now leans toward wrong, she is not a fraud. She is a scientist holding a stubborn result that the rest of her field cannot reproduce and will not accept, which is one of the loneliest places a researcher can stand. And the history of science is full of people who have stood there, some later vindicated, most not. If the WIMP is not turning up, in the colliders, or in the sky, or in the cathedrals of silence underground, then perhaps the dark matter is some other kind of particle entirely. And the leading alternative has a strange and almost comic origin. It is called the axion, and it was not invented to explain dark matter at all. In 1977, two physicists, Roberto Peccei and Helen Quinn, were trying to solve an unrelated puzzle in the theory of the strong nuclear force, the force that binds the cores of atoms. The equations of that force contain a term that, by all rights, ought to cause a certain subtle asymmetry in nature, a difference between matter and its mirror image in the behavior of particles. But experiments show that asymmetry is absent, or so tiny it has never been seen. Why the term should sit so precisely at zero was a genuine mystery, and Peccei and Quinn proposed a mechanism that would naturally drive it there. Their mechanism implied the existence of a new particle. When two other physicists, Frank Wilczek and Steven Weinberg, worked out the consequences, Wilczek gave the particle its name. He called it the axion, after a brand of laundry detergent, because it cleaned up the problem. The name stuck. There is a quiet elegance to how this candidate arose, and it is the same elegance that once recommended the WIMP. Nobody set out to invent a dark matter particle. Peccei and Quinn were trying to understand why the strong force is so peculiarly well behaved, why it does not produce an asymmetry that the equations seem to permit. The particle they were led to was a byproduct, a consequence of the fix rather than its goal. And then, years later, when cosmologists worked out how such a particle would have been produced in the early universe, they found that it would have been made in roughly the right amount, and would be cold and slow and spread through space exactly as dark matter must be. So the axion, like the neutralino before it, is a candidate that two separate branches of physics seem to be pointing at without coordinating. That kind of accidental convergence is rare, and it is precisely what makes physicists suspect there may be something to it. The axion, if it exists, is the opposite of the WIMP in almost every way. It is not heavy, but absurdly light, perhaps 1 trillion times lighter than a single proton, and there would not be a few of them drifting about. There would be an ocean of them, vast numbers filling all of space, produced not by the freeze-out that makes WIMPs, but by a different process in the early universe, a kind of settling of a cosmic field, which would have left behind exactly the sort of cold, slow, gently spread substance that dark matter needs to be. So the axion arrives from a completely different corner of physics, solving a completely different problem, and yet it, too, could be the dark matter. That is the kind of coincidence that makes physicists pay attention. Catching an axion requires a completely different kind of instrument, and the idea behind it, proposed by the physicist Pierre Sickevi, is wonderfully strange. An axion, in a strong enough magnetic field, can very occasionally transform into a particle of light, a single faint photon, at a frequency set by the axion's mass. So you build, in effect, an exquisitely tuned radio receiver, a metal cavity sitting inside a powerful magnet, and you listen for a whisper of radio power appearing out of nowhere at one precise frequency. The flagship of this effort, the Axion Dark Matter Experiment at the University of Washington, led for years by the physicist Leslie Rosenberg, has been doing exactly this for more than 2 decades. The difficulty is that no one knows the axion's mass, which means no one knows which frequency to tune to. So the search proceeds one narrow band at a time, the cavity retuned, the listening repeated, slowly sweeping across the dial of possible masses, a process that can take years to cover even a modest range. Graduate students sit the night shifts, watching the apparatus, checking for anomalies that almost never come. No axion has been heard yet. But unlike the WIMP, the axion's hiding places have barely been searched, and the hunt is in a sense, just beginning. Other versions of the search use the sun as the source, hunting for axions made in the solar core, or try to conjure axions in the laboratory by driving an intense laser through a magnetic field and watching for the few that pass, ghost-like, through a solid wall. None has caught one, but many physicists now regard the axion as the most promising candidate left standing. There is a stranger cousin of the axion worth mentioning, because it has gathered interest as the WIMP has faded. If the dark matter particle were not merely light but unimaginably light, far lighter even than the ordinary axion, its quantum nature would begin to show on astronomical scales. Such a particle would behave less like a swarm of tiny pellets and more like a single vast wave, its quantum ripples large enough to fill the core of a galaxy. This idea, sometimes called fuzzy dark matter, would naturally smooth out the sharp central spikes that the cold dark matter simulations predict, and that real galaxies seem to lack, replacing them with gentle, wave-like cores. It is speculative, and it is hard to test, but it is a reminder of how wide the field of possibilities still is. Dark matter could be heavier than a proton or lighter than a billionth of one. We have searched a sliver of that immense range and found nothing, and the rest waits. And there is the sterile neutrino, the warm candidate we met earlier. The ordinary neutrinos that stream through us by the trillion are already nearly invisible, interacting only through the weak force and through gravity. A sterile neutrino would be a heavier, even shyer relative, interacting through gravity alone, mixing only faintly with its ordinary cousins. Produced in the right amount in the early universe, it could be the dark matter, and being moderately fast, it would be warm rather than cold, softening some of the small-scale tensions the cold models run into. It was a sterile neutrino, slowly decaying, that the faint and disputed X-ray line once seemed to promise. The promise has not been kept, but the candidate remains alive, one more reasonable shape the unknown could take. There have been other candidates too, raised and tested and mostly set aside, and they are worth knowing because they show how thoroughly the simplest ideas have been examined. For a time, many hoped the dark matter might just be ordinary objects too dim to see, dead stars, drifting planets, the cold leftovers of stellar life, lurking in the halo of the galaxy. Such objects were given the deliberately rival name MACOs, massive compact halo objects. Set against the WIMPs, they could be hunted by a beautiful trick of relativity. When such an object drifts in front of a distant star, its gravity briefly magnifies the star's light, a momentary brightening that rises and falls over days or weeks in a precise, predictable shape. Through the 1990s and beyond, several teams watched millions of stars night after night, in our galaxy's halo and toward our neighbouring galaxies, waiting for those flickers. They monitored star fields so vast that the work could only be done by automated telescopes and early computers, sifting the steady light of millions of stars for the rare one that brightened and faded in the signature way. They saw some. They saw enough to prove the method worked, and to find genuine dark objects drifting in the halo. But they did not see nearly enough to account for the dark matter. The dim, ordinary objects exist, but there are too few of them. Counting every flicker, the halo could not be more than a small fraction made of such things. It had to be something else. More recently, black holes formed in the first instance after the Big Bang have been raised as another possibility, briefly revived when gravitational wave detectors began finding black holes of unexpected size. Though careful study, much of it using the same microlensing surveys, has now closed off most of the mass ranges where such primordial black holes could account for everything. One by one, the ordinary explanations have been weighed and found wanting. Whatever dark matter is, it appears to be genuinely new. Through all of this, one piece of evidence stands somewhat apart, because it does not depend on any particle theory at all. It does not ask what dark matter is made of. It simply shows, almost beyond argument, that there is real, invisible mass present in a place where you can see it sitting apart from everything that gives off light, and it comes from watching what happens when light passes near a great concentration of mass. One of the predictions of Einstein's theory of gravity, published in 1915, is that mass bends the path of light. A ray passing close to a heavy object is deflected, its course curved by the way the mass warps the space around it. The effect was first confirmed in 1919, when an expedition led by Arthur Eddington photographed stars near the Sun during a total eclipse and found their apparent positions shifted by exactly the tiny amount Einstein's equations demanded. It was the observation that made Einstein famous overnight. The principle behind it is worth holding on to because it is what makes dark matter visible at all, in the only way it ever becomes visible. Light, left to itself, travels in straight lines, but mass curves the space that light travels through so that near a heavy object the straight line itself is bent and a ray of light passing by is deflected from its course. The light does not care whether the mass that bends it glows or not. It responds only to the mass, to the warping of space, to gravity, and that is the gift, a substance that gives off no light, that cannot be seen by any direct means, still bends the light of everything behind it, because it still has mass, and mass still curves space. So we cannot see the dark matter, but we can see the distant universe warped as its light passes through the dark matter on the way to us, and from the precise pattern of that warping we can reconstruct where the unseen mass lies and how much of it there is. It is the closest thing we have to a photograph of the invisible. Scaled up, this same bending turns a massive object into a lens. The light from a distant galaxy, passing through the gravity of a closer cluster of galaxies, gets bent and smeared into arcs, rings, and multiple images. The phenomenon is called gravitational lensing, and the first person to suggest that clusters of galaxies could act as such lenses was, once again, Fritz Zwicky in 1937, who pointed out that the effect could be used to weigh a cluster directly, without assuming anything about its internal motions. It took more than 40 years for the technology to catch up to him. The first such lens was discovered in 1979, a single distant quasar split by a closer galaxy into what looked like twins. By the 1990s, the Hubble Space Telescope was photographing whole clusters surrounded by delicate luminous arcs, each arc the stretched and brightened image of a galaxy far behind the cluster, its light bent on the way to us. That first twin quasar caused real confusion when it was found, because the two images were so alike, the same colour, the same spectrum, the same flickering, that astronomers at first wondered whether they were looking at a strange pair of identical objects. They were not. They were two images of one object, its light split into two paths around an intervening galaxy and bent back together toward the Earth. The first gravitational lens ever confirmed, 60 years after Zwicky said such things should exist. Once astronomers knew what to look for, the lensed arcs began turning up everywhere. The great telescopes pointed at massive clusters, thin curved smears of light wrapped around the cluster cores, the distorted images of a more distant universe. And every one of those arcs was a measuring device. Its exact curve set by the total mass of the cluster bending it, the dark mass included, whether it glowed or not. Those arcs carry information. Their size and shape and position depend on the total mass of the cluster doing the bending, including every scrap of dark matter, because dark matter bends light exactly as ordinary matter does. By modelling the arcs, astronomers can map the mass of a cluster, the seen and the unseen together. And this method does not care about velocities or about whether the cluster is settled and stable. It rests only on the geometry of warped space and the well-tested laws of gravity. It is, in effect, a way of weighing the invisible by watching its shadow fall across the light of more distant things. When astronomers applied it to clusters, the mass it revealed was, again, far larger than the visible galaxies and gas could supply. The dark matter was there, written in the arcs. When the alignment between a distant galaxy, a foreground mass, and the Earth is very nearly perfect, the lensing produces something even more beautiful, a complete, or nearly complete, ring of light, the distant galaxy smeared all the way around the closer one. These are called Einstein rings, after the man whose equations predicted them, though Einstein himself thought the alignment so unlikely that the rings would never actually be seen. Dozens are now known, each a small monument to the warping of space, and each a precise scale on which the mass of the foreground object, dark matter included, can be weighed. But the most powerful version of this technique is also the most subtle, and it does not need a perfect alignment or a dramatic arc. Every distant galaxy whose light passes through the universe on its way to us is bent, just slightly, by all the mass it passes near. The effect on any single galaxy is far too small to notice. A galaxy is squashed by perhaps 1%, far less than its own natural irregularity of shape. But if you measure the shapes of millions of distant galaxies across a wide patch of sky, the random irregularities average out, and a faint, coherent distortion remains, a gentle combing of the galaxy's apparent shapes that reveals the mass lying between them and us. This is called weak lensing, or cosmic shear, and it has become one of the central tools of modern cosmology. Great surveys photograph enormous swaths of sky, measure the shapes of vast numbers of faint galaxies, and from the subtle alignment of those shapes, reconstruct a map of all the mass in the foreground, glowing and dark together, spread across the universe. The maps that result show the same cosmic web the simulations predict, traced out not by light but by the bending of light, the invisible scaffolding made faintly visible at last. But the single most convincing image in the entire history of dark matter came from a cluster that had been torn apart in a collision, and is still flying apart as we watch. The bullet cluster lies about 3.7 billion light-years away, and it is not one cluster but two, caught in the act of passing through each other. The crossing happened, in cosmic terms, recently, and we are seeing the aftermath, the two clusters separating again after the impact. And the value of this particular wreck is that a colliding cluster sorts its contents out by their nature, like a centrifuge. A galaxy cluster is made of three things. There are the galaxies themselves, which are tiny compared with the gulfs between them, so that when two clusters collide, the galaxies mostly sail straight past one another untouched, like two swarms of bees flying through each other. There is the hot gas between the galaxies, which actually holds most of the ordinary mass of a cluster, and which behaves completely differently. When two clouds of gas meet, they cannot pass through each other. They crash, they drag, they pile up in the middle, slowed by the collision, and left behind as the galaxies race ahead. And then there is the dark matter. The question the bullet cluster answers is, simply, where did the dark matter go? If dark matter is a real substance made of weakly interacting particles, it should behave like the galaxies, not like the gas. It should pass straight through the collision almost untouched and stay out ahead, moving with the galaxies, leaving the slow ordinary gas behind in the middle. But if there is no dark matter at all, and the missing mass is really a sign that we have misunderstood gravity, then the gravity should simply follow the ordinary matter, and since most of the ordinary matter is in that stranded central gas, the gravitational pull should be centered there, on the gas. In 2006, a team led by Douglas Clow and Maxim Markovich settled it with two overlaid maps. With the Chandra X-ray Observatory, they mapped the hot gas, glowing in X-rays, and found it where expected, piled up and stranded in the center of the collision. Then, using gravitational lensing, the bending of light from galaxies far behind, they mapped where the mass actually was, the total gravity of the system. The two maps did not sit on top of each other. The mass was not with the gas. It was out ahead, on either side, sitting with the galaxies that had passed cleanly through. The dark matter had sailed through the collision untouched, exactly as a substance of weakly interacting particles should, and it had pulled away from the ordinary gas that held most of the visible matter. You could point at one part of the image and say, there is most of the ordinary matter, and point at a different part and say, there is most of the mass, and the two were in plainly different places. Markovich later described the moment the lensing map was laid over the X-ray image, the displacement obvious at a glance, not subtle, not a matter of careful statistics, just visibly there. The bullet cluster did not prove dark matter beyond all conceivable doubt, because science does not deal in final proofs, but it came as close as this kind of astronomy ever does. It is very hard to explain a place where the mass and the visible matter have come apart, unless there is some invisible substance carrying that mass. And the bullet cluster is not alone. Since that first image, astronomers have found other colliding clusters showing the same separation. The mass pulled ahead with the galaxies, the ordinary gas stranded behind. There is one famous and unusual case, a system sometimes called the train wreck, where the geometry came out so tangled that for a while it seemed to show the mass in the wrong place, and the modified gravity camp seized on it, and the dark matter camp had to work hard to understand the complicated three-way collision that produced it. That is healthy. A single clean example can be a fluke or a misreading. A growing collection of them, most pointing the same way, with the awkward cases eventually understood, is how a conclusion hardens. Each merging cluster is a natural experiment performed on a scale no laboratory could ever match. Two cities of galaxies thrown through each other at millions of kilometers per hour, and we get to walk through the wreckage afterward and sort the visible from the invisible. Most of the time, the mass is not where the light is. The mass is somewhere else, and it is real. The lensing tells us one more thing. Beyond the bare fact that the dark matter exists, the way it sails through these collisions untouched, never slowing, never heating, never piling up like the gas, means that dark matter barely interacts, even with itself. It feels gravity, and perhaps the faintest whisper of some other force, but essentially nothing else. It is, in the most precise sense, a ghost, passing through itself and through everything else, betrayed only by the weight it carries. That is a clue, and a frustrating one, because it is exactly the property that makes it so nearly impossible to catch. The very thing that lets it slip through a light year of lead is the thing that lets it slip through every detector we build. Which brings us, finally, to the most radical possibility of all, the one that asks whether we have been wrong from the very beginning. Not wrong that something strange is happening, the bullet cluster makes that impossible to deny, but wrong about what kind of strangeness it is. What if there is no invisible substance, and what we are seeing is instead a flaw in our understanding of gravity itself, in the law that Newton wrote down and Einstein refined? To take that idea seriously, we have to go back to a quiet theorist in Israel who, in the early 1980s, looked at the very same flat rotation curves that Vera Rubin had measured and drew a completely different conclusion. His name is Mordechai Milgrom, and in 1983, working at the Weizmann Institute, he proposed something heretical. He was not trying to overthrow dark matter for its own sake. He had noticed a pattern in the rotation curves that the dark matter idea did not naturally explain, a tight relationship between how fast the flat part of a galaxy's curve turns and how much ordinary, visible matter the galaxy contains. The more luminous the galaxy, the faster the rotation, and the relationship is remarkably clean, holding across an enormous range of galaxy sizes. In the dark matter picture, this tidy relationship is something of a happy accident, requiring the invisible halo and the visible galaxy to be matched in just the right proportions. Milgrom wondered whether it might instead be a clue to a deeper law. His proposal is called modified Newtonian dynamics. The idea is that the familiar relationship between force and motion, the rule that a given push produces a given acceleration, holds perfectly well at ordinary strengths of gravity, the kind we feel on Earth or in the inner regions of a galaxy. But at extraordinarily low strengths of gravity, weaker than anything we ever encounter in daily life, far weaker than the sun's grip on the most distant planet, the rule changes. At those tiny accelerations, gravity becomes a little stronger than the old law predicts. And the threshold where this kicks in is so faint that we would never have stumbled across it in the solar system, where gravity is always overwhelmingly strong by comparison. But out at the edges of galaxies, where the pull has grown vanishingly weak, the modified rule would take over, and the rotation speeds would flatten out on their own, with no need for any invisible mass at all. What is undeniable is that, on the scale of single galaxies, this idea works astonishingly well. Feed Milgrom's rule a galaxy's visible matter alone, and it reproduces the rotation curve, the flatness, the tight relationship between brightness and speed, often more cleanly than dark matter models that have to be fitted with carefully shaped invisible halos. Decades later, astronomers led by Stacy McGarr sharpened this into something called the radial acceleration relation, showing that across a huge sample of galaxies, the acceleration you actually measure at any point is fixed, with very little scatter, by the ordinary visible matter alone. In the dark matter picture, where the invisible halo is supposed to dominate the outer galaxy, that cleaner relationship between motion and visible matter is a puzzle still being argued over. It is one of the genuinely open tensions in the field, and it is the strongest card the modified gravity idea holds. Researchers have even tried to test the idea closer to home by examining pairs of stars orbiting each other at enormous separations, so far apart that the gravity binding them dips below Milgrom's threshold. If gravity changes at very low accelerations, these wide stellar pairs should orbit slightly faster than ordinary gravity predicts, with no dark matter anywhere near to muddy the test. The European Gaia spacecraft, with its precise measurements of stellar motions, has made such tests possible for the first time, and several teams have attempted them. The results, so far, conflict. Some groups report a hint of the modified behavior, others report none, and the measurement is so delicate, so vulnerable to hidden companion stars and subtle errors, that no one yet regards it as settled. It is a live and genuinely contested frontier, one of the few places where the two great theories might be told apart in our own galactic neighborhood, rather than across billions of light years. The dark matter model has its own troubles on these small scales, the ones we noted earlier. The simulations predict sharp, dense spikes of dark matter at the centers of galaxies, where many real galaxies show gentle cores. They predict far more small satellite galaxies around the Milky Way than we actually find. And the most massive satellites the simulations predict seem too dense and too substantial to match the modest galaxies we see, a mismatch with the blunt name too big to fail. None of these is fatal, and ordinary explanations exist for each. The messy physics of exploding stars and stripped gas, reshaping the centers of galaxies, small satellites too faint to have been counted until very recent. Deeper surveys began turning them up. Indeed, as telescopes have improved, more and more of those faint missing satellites have actually been found, dim little galaxies that earlier surveys simply could not see, and the gap between prediction and observation has narrowed. But the modified gravity camp points to these tensions, fairly, and asks why the simplest version of dark matter keeps stumbling exactly where the alternative succeeds. The honest answer is that the messy physics of ordinary matter, of gas and stars and explosions, is genuinely hard to simulate, and much of the disagreement may live in that difficulty rather than in the nature of the dark matter itself. But the questions are real, and a good theory does not pretend its open problems away. The trouble for modified gravity begins the moment you leave single galaxies behind. Apply Milgrom's rule to a whole cluster of galaxies, the same kind of system where Zwicky started this entire story, and it helps, but it does not finish the job. Even with the modified law, a cluster still appears to hold more mass than its visible matter can supply. The Coma cluster, Zwicky's original target, still demands something unseen, even under the new rule. The amount is smaller, but it is not zero. The modified gravity supporters suggest the remaining gap could be filled with ordinary matter we simply have not detected, or with neutrinos. But those patches bring their own problems, and the cluster gap is one of the strongest arguments against the idea standing alone. The bullet cluster is harder still for modified gravity. If there is no dark matter, and gravity simply follows the ordinary matter, then the pull of that torn-apart cluster should be centered on the stranded gas in the middle, where most of the ordinary matter sits. But the lensing shows the mass out ahead, with the galaxies divorced from the gas. That is natural if the mass is a ghostly substance that passed through the collision. It is very awkward if the mass is just a feature of where the ordinary matter is, because the ordinary matter is mostly in the wrong place. Defenders of modified gravity have made arguments about the collision being unusually fast, or the analysis resting on assumptions about the cluster's shape, but those arguments have not won over the wider field. And the deepest difficulty comes from the early universe, from that ancient background light again. The pattern of peaks in the background radiation depends on the interplay between ordinary matter and dark matter in the primordial plasma, and the dark matter picture predicts the heights of those peaks naturally, including the crucial third one. To make the modified gravity idea say anything at all about the early universe, theorists like Jacob Bekenstein had to build it out into a full relativistic theory, a much heavier construction than Milgrom's original rule. Those constructions struggled to reproduce the pattern of the background light without quietly reintroducing some form of dark matter anyway. And then, in 2017 came a sharper blow. When two neutron stars collided more than 100 million light-years away, detectors caught both the ripples in space-time from the crash and the flash of gamma rays it released, and the two arrived within seconds of each other after traveling for over 100 million years. That near-perfect tie meant that gravity travels at the speed of light, to staggering precision. Several of the leading relativistic versions of modified gravity had predicted that gravity should travel at a slightly different speed. Those versions were ruled out, in an afternoon, by a signal from two dead stars. It is worth noticing how that worked, because it shows science at its most ruthless and its most fair. The modified gravity theorists had made a genuine testable prediction that gravity and light should travel at slightly different speeds, and for years there had been no way to check it. Then nature performed the experiment. 2 neutron stars, in a galaxy more than 100 million light-years away, spiraled together and crashed, sending out both a tremor in the fabric of space and a burst of light. The 2 signals raced across more than 100 million years of cosmic distance and arrived at the Earth less than 2 seconds apart. If gravity travelled even fractionally slower than light, that tiny gap would have grown over such an immense journey into a vast separation. It did not. The 2 arrived together, and a whole family of theories died that day, killed cleanly by a single observation. That is the bargain science makes. A theory earns its keep by sticking its neck out, and the universe is under no obligation to be kind to it. So modified gravity is not dead, but its simplest and most studied forms are in serious trouble, and the weight of all the evidence taken together now leans hard toward a real substance over a flawed law. The bullet cluster, the background light, and the speed of gravity together build a case that is very hard to escape. And yet Milgrom is not the villain of this story. He is a scientist who looked honestly at the same data as everyone else and reached a different conclusion, and defended it with rigour for 40 years, and in doing so forced the dark matter camp to sharpen its arguments and confront the small-scale problems it might otherwise have brushed aside. The field is sharper for his stubbornness, even if most cosmologists now believe his specific answer is wrong. That is how the thing is supposed to work. The universe does not care which theory is more elegant, or which of its champions is more pleasant. It is simply what it is, and the work is to keep asking, and keep measuring, and keep listening, even when the answer is slow in coming. So where does that leave us? After 90 years of measurement, beginning with Zwicky and his 8 galaxies and ending with detectors that can feel the nudge of a single nucleus a kilometre underground, the honest assessment is two-sided, and the 2 sides do not resolve into one. On one side, the evidence that dark matter exists is overwhelming, and it has only grown stronger with time. On the other, the evidence that we know what it is has been tested, again and again, and has come up empty. We can hold both of these at once, and we have to, because both are true. We know the substance is there. We know it from the Coma cluster, where Zwicky measured it in 1933 and was disbelieved for 40 years. We know it from the flat rotation curves of spiral galaxies, which Vera Rubin and Kent Ford found turning where nothing should have been turning, confirmed by the radio astronomers tracing cold gas out into the dark. We know it from the oldest light in the universe, whose pattern of peaks fixes the recipe of the cosmos to within 1% or 2. We know it from the early chemistry of the universe, which independently pins down how little ordinary matter there is. We know it from the bending of starlight around clusters, and most vividly from the bullet cluster, where the mass was caught sitting apart from the matter that gives off light. And we know it from the simple fact that the galaxies exist at all, that there was time for them to form, which there would not have been if dark matter had not gone ahead and dug the wells. No single one of these would be enough to compel belief on its own. Any one measurement could be questioned, any one method could harbour a hidden flaw. But they do not stand alone. They lean on one another, 6 or 7 independent pillars, raised at different times by different hands, each resting on different physics, and all of them holding up the same conclusion. That is what a robust scientific fact looks like. Not a single dramatic proof, but a quiet, overwhelming convergence that becomes harder to doubt the longer you look at it. The existence of dark matter is, by this measure, one of the best established facts in all of astronomy. It is its nature, and its nature alone, that remains entirely open. And we do not know what it is. We do not know whether it is a single kind of particle or a whole hidden family of them, with their own forces and their own structure, a dark sector running in parallel to our own. We do not know whether it is the heavy WIMP, hunted for 40 years and never found, or the feather-light axion, barely searched, or something no one has yet thought to propose. We do not know how it was made in the first instance, except in rough outline. We do not know whether it is perfectly stable, or whether, on some time scale, far longer than the present age of the universe, it slowly comes undone. It is worth being clear about what would change if we found out. If a detector deep underground finally registered the unmistakable signature of a particle from the galactic halo, or a radio cavity caught the faint note of an axion, It would not just fill in a blank in a textbook. It would mean that most of the matter in the universe belongs to a kind of physics we have never directly touched. A new layer of reality sitting alongside the one we have spent 4 centuries mapping. It might be the first thread of a whole hidden sector, with its own particles and perhaps its own forces, as rich as the familiar world but dark to us. The discovery of what dark matter is would likely rank among the largest in the history of physics, comparable to learning that atoms were not the smallest things, or that space and time could bend. And the strange truth is that it could happen next year, in an experiment already running, or it could remain out of reach for another generation. No one knows which. The instruments are listening right now, tonight, while you lie in the dark, and they may hear nothing for decades, or they may hear something tomorrow. The room is still dark. Outside, the night has deepened. The hum of the world has faded further, or perhaps stopped altogether. And you are still here, in the quiet. The particles are still passing through you, billions of them every second, as though your body were not there. They come from the halo of the Milky Way, the great invisible sphere that wraps our galaxy and reaches far past its glowing edge. They come from the deep structure of the cosmos, from a web that was already taking shape in the first fraction of a second after the Big Bang. They have been travelling for the whole age of the universe, and they will go on travelling long after the last star has cooled and gone out. Think, for a moment, of the journey of just one of them. It came into being in the first instant after the Big Bang, before there was light to see by, before there were atoms, when the universe was a fraction of a second old. It has drifted, ever since, through the slow gathering of the cosmic web, through the formation and death of generations of stars, through 13 billion years of cosmic history, untouched, unchanged, interacting with nothing. It helped, with countless others like it, to dig the gravitational well in which our galaxy formed. It has circled the center of the Milky Way many times over, and tonight, at the end of all that, it passes through the room where you are lying, through the air, through your body, and out the other side, and continues on into the dark, having left no mark, having felt nothing, on its way to the next 13 billion years. It does not know you are here. It does not know anything. It is simply matter, the oldest and most abundant kind, passing through. We have given the substance a name, dark matter, and the name is honest in its way, because it names exactly what we do not know. The next generation of instruments is already coming online to learn more. A great new telescope in the mountains of Chile, the Vera Rubin Observatory, named for the woman who made the case undeniable, has begun surveying the southern sky, and over the coming years it will map the distribution of dark matter across the heavens with a precision she could only have dreamed of by measuring the faint bending of light from countless galaxies. It will not tell us what the dark matter is. That answer, if it comes, will come from underground, from the cathedrals of silence and the patient radios tuned one frequency at a time. But it will tell us, in extraordinary detail, where the dark matter is and how it moves and how it shaped everything we can see. There is something fitting in that observatory carrying her name. Rubin spent her life measuring where the invisible mass lay, galaxy by galaxy, one careful curve at a time, and being asked, again and again, to prove that what she had measured was real. The telescope named after her will do the same work she did, on a scale she could not have attempted, photographing the whole southern sky over and over for a decade, weighing the dark matter across billions of galaxies by the faint distortion of their light. It is, in a sense, her method made enormous, the patient mapping of the unseen, carried out by a machine that will gather more data in a few nights than she could have collected in a lifetime. She did not live to see it open its eye, but the eye is open now, and it is looking exactly where she taught the field to look. Vera Rubin, near the end of her life, used to say how little we truly know about the universe, and she did not say it with despair. She said it with something closer to relief, the recognition that the cosmos is larger and stranger than our theories of it, and that the right response to that strangeness is not to look away, but to look harder. She died in 2016, at the age of 88, before the observatory that carries her name had opened its eye. The substance she helped find was here long before any of this. It was here before the first star, before the first galaxy, before the ancient light was set free. It was here when the Earth gathered out of dust, when the first living things stirred, When the first human being looked up and wondered what the lights were made of, it is here now, in this room, moving through you, through the walls, through the floor, through the dark air. It asks nothing of you. It has no purpose and no awareness. It is simply the larger part of the universe, the part we cannot see, and we are only at the beginning of understanding how much we still do not understand. There is no need to resolve any of it tonight. The question has waited 100 years already, and it will wait until morning and longer. Somewhere, in a hall carved out of rock a kilometre beneath a mountain, a detector colder than deep space is still listening, as it will listen all through the night for a single nudge that may or may not come. Somewhere, a radio cavity is sweeping slowly across the dial of possible frequencies, one narrow band at a time. The work goes on while the world sleeps, patient and unhurried, because the thing it is chasing has been patient too, drifting through everything for the entire age of the cosmos, in no apparent rush to be found. The darkness outside is not empty. It never was. Good night.